Last class we defined a Taylor polynomial for a function, which was just a polynomial that's derivatives matched the function. Today we care about how close these Taylor polynomials are to the actual function. And so in other words, how useful of approximation are they actually? And so let's consider trying to approximate the function f of x with a Taylor polynomial. In order to do that, we're going to need to assume that f has n plus 1 continuous derivatives. Then we're going to say that we're approximating f with Tn of x. And so that's a Taylor polynomial of degree n. And so the last term in this should be an x to the n. And then we're going to assume that the Taylor polynomial is centered at x equals a. So that just tells us the point where the derivatives agree with the original function. And then just for notation, we're going to call Rn of x the error when you use t to approximate f. And so in other words, we're going to define f of x to be equal to Tn of x plus Rn of x. And so Tn is the polynomial, again, that we're using to approximate it. And then R is just the leftovers, whatever those are. And so that is the error. And now we want to figure out a way of bounding Rn of x, or in other words, the error when we use t. And so it turns out that we can write down a relatively nice formula for the error. And so we could write the error as the absolute value of the difference between f and t. And so that's just how close f is to the Taylor polynomial. And then according to the notation that we just decided on, that's the same as Rn of x. So that's just our notation for the error. And then it turns out that the formula that we get looks awfully similar to the error bounds that we had a while ago for Simpson's rule and the trapezoid rule. And so that means that we're going to have some term that involves the n plus first derivative of f. And so the first expression here is the maximum of that n plus first derivative between the center of the series, which is a, and the point that we're actually plugging into the function, which is x. And so this will be the complicated part of finding error bounds typically. And then after that, we just have this numerator right here, which is the difference between the point that we plug in, x, and the center of the series, a, raised to the n plus first power, and then we just divide by n plus 1 factorial. So let's look at an example of how these parts work together. And so say that we're trying to approximate sine of 0.1 with a Taylor polynomial. And more specifically, in this case, we're going to use t3 of x centered at x equals 0. And so in order to find an approximation for sine of 0.1, I'm going to want to start by finding t3 of x. And we've already seen the Taylor series for sine of x. And so that should just be equal to this sum right here from n equals 0 to infinity of x to the 2n plus 1 times minus 1 to the n plus 1, or sorry, just minus 1 to the n there, over a 2n plus 1 factorial. And so eventually we're going to want to memorize the Taylor series for sine and cosine and a couple other common series because we'll end up using them so much. But that is the one for sine of x, or in other words, it's just the odd powers of x. And so here, if we want to figure out what t3 of x is, then we just have to write out the first few terms of this series until we get an x cubed term. And so in this case, if I write out the n equals 0 term, that just gives me x. And if I write out the n equals 1 term, that ends up giving me a negative x cubed over 3 factorial. So I've already arrived at the x cubed term, and I'm already done. And at this point then, all I need to do is plug in 0.1 into this expression, and that'll be my estimate for sine of 0.1. So I'm hoping that sine of 0.1 is relatively close to this, which would be 0.1 minus 0.1 cubed over 3 factorial. And I want to write out what this is by hand so that I can see what this estimate would give me. So 0.1 is just 1/10. 0.1 cubed is 1/1000th. And then 3 factorial is 6. And now if I simplify this a little bit, it ends up being 599 over 6,000. And so that's my estimate for sine of 0.1. At this point though, I have no idea how good of an estimate 599 out of 6,000 is for the actual value of sine. And so here I'm going to need to use this error bound formula in order to figure that out. And so the first step in the error bound formula would be to figure out the fourth derivative of x. And that's just because we used t3, and so we want one more derivative than the polynomial that we used. And so for sine of x, if I take 4 derivatives, I just get sine of x back. And so now I need to figure out the maximum of sine of x in absolute value on the range where x is between the center of the series, which in this case was x equals 0, and the value that I'm plugging in, which in this case is 0.1. And so because sine is an increasing function on this range, it's really true that the best maximum I could write down is just sine of 0.1. But that's not going to be a very helpful bound here because I'm already trying to approximate what sine of 0.1 is, and I don't know what that value is exactly. And so instead, it'll be fine if I'm a little less precise with my bound, and instead I just say that I know that sine is always less than 1. And that'll be fine for here. And so if I use that, then I know that R4 of x, or sorry, R3 of x, because we're using T3, so we want to bound the error for R3, and that should be less than or equal to this maximum that I just computed, so I'll plug in 1 here, and then I want to multiply by the absolute value of x minus a, so x is the point that I'm plugging in, and a is the center of the series, and then I'm raising this to the n plus first, and in this case n was 3, so I'm raising it to the 4th power, and then I'm dividing by 4 factorial. And so if you simplify this out a little bit, then you'll end up getting 1 over 240,000, which ends up being approximately 4.2 times 10 to the minus 6. And so that's telling you that just using those first 2 terms from the Taylor series, or the x minus x cubed over 3 factorial, is already giving you at least 5 digits of accuracy for sine of 0.1. And so we can check that by using a calculator to evaluate these values. And it turns out that sine of 0.1 is actually equal to 0.0998334, and so on. And if you compute what 599 over 6,000 is, that ends up being 0.099833, and so on. And so it's not until this next digit right here, the one after what I wrote, so this 3 right here, that they actually differ for the first time. And so you can see that these are extremely accurate to begin with.